All right, let's continue. So what we did in the previous segment was introduce the notion of the bi-unit domain and use that to define our basis functions, right? And specifically, we are working with linear basis functions in this simplest of finite element formulations, right? And we've gone ahead and defined those basis functions. And at the end of the segment, we also talked about, we observed that these basis functions have this Kronecker delta property. Okay, so these basis functions also have another property which is useful to note also, right? So let's do the following. Let's consider n1 at some arbitrary point c in the bi-unit domain plus n2 at c. Very trivially, or very simply, this is 1 minus c over 2 plus 1 plus c over 2, which is 1. Okay? So at any point in the domain, these basis functions add up to 1. This is important because it make sure that we can at the very least represent constants. Okay, so this is an important property. The other thing I should mention now is that the way we've written these functions can be generalized, and we will do this later. We can generalize these to higher order polynomials, generalizable, because I'm not quite sure that's a word. Anyway, it's generalizable to higher order polynomials. Okay, and in generalizing them to higher order polynomials, we are going to do it, the time has not come to do it, we'll do it later after quite a few more segments, but when we do that, we will do so by observing that these are linear basis functions of a class of polynomials called Lagrange polynomials. Okay, so they're generalizable to higher order polynomials, and they are drawn from a family of polynomials that are called Lagrange polynomials. Okay, we'll do that later, not right now. Yet another thing I want to point out about these basis functions. Let me see, that's a bullet point, and this is another bullet point. Okay, yet another bullet point. If we look at these basis functions, and for just a minute, I'm going to go back to our physical domain. Okay, so let's suppose we have element here. This is element omega e, and next to it we have element omega e plus 1, omega e plus 2 next to it, right, and so on. Now, we focused upon a specific or really an arbitrary element E in order to construct these basis functions, and we did that by going into the bi-unit domain. First of all, we need to recognize that each of these elements in the physical domain is obtained from this bi-unit domain, c equals minus 1, c equals 1. And in this bi-unit domain, we are going to denote as omega c, okay, for obvious reasons. So note that each or an arbitrary element omega e or omega e plus 1, or whichever one we want, is always constructed as a mapping from the same element in the bi-unit domain, right? The same parent element, as it is sometimes called in the bi-unit domain. Okay, once we do this, we get our basis functions in the physical domain, and I want to draw them, which I want to do in a different color here. Okay, so in the physical domain, if we look at element omega e, we'd have this basis function, right, and that one. Okay, if we look at omega at element omega e plus 1, we have also similar looking basis functions, right? But what happens here is that they are defined over element omega e plus 1, right, and so on, right? Now, if we look at how these basis functions appear together in the physical domain, let's focus on the fact that here we have node x e plus 1. We may choose to look at these basis functions in the physical domain as being located at global node xe plus 1. When I say global node xe plus 1, what I mean is that I'm looking at this node as being one of the nodes in the overall domain omega, right? So I may look at xe plus 1 as a global node. Okay, and in fact, it has global node number e plus 1, right? If you were to look at that same nodal point in the context of element E, okay, you would call it local node number 2 for element E, okay? Okay, it is also the local node number 2 for omega E, okay, and it is local node number 1 for element omega E plus 1. Right? This is nomenclature that we will use later on as we advance with our finite element formulation. Nevertheless, the point I wanted to make here is that now when we look at this collection of basis functions and we focus upon the individual nodes and view them as global nodes on a sort of global scale, right, with global node numbers, what you observe is that we have for node xe plus 1, we have a basis function which I'm going to draw slightly off. I'm going to sort of emphasize it, and I'm drawing it in red, but it's slightly off the actual line describing the basis functions, right? And I'm doing that just so that you can see the underlying element level basis functions, which when put together give us what may be called a basis function corresponding to node xe plus 1, okay? Now, the basis function corresponding to node xe plus 1, which I will label, right, this is the basis function for global node E plus 1. Observe that the basis function corresponding to global node E plus 1 has a very local sort of sphere of influence. It is non-zero only on the elements that are immediately adjoining node number E plus 1, global node number E plus 1. Okay, so the basis function for global node E plus 1 is non-zero only in elements omega E and omega E plus 1. We may choose to regard the basis function corresponding to global node number E plus 1, this red hat function that I have outlined here, we may choose to regard it as a globally defined basis function. However, its support is very local. Its support is local to the two elements, in this case, adjoining the node of interest. Okay? So this property is referred to as local support sorry, not local, sorry, it's called compact support property, sorry. Compact support. Compact support of global basis functions. Okay, the idea here is that our in constructing our finite element formulation, it is convenient to focus upon our element subdomains, and by invoking this idea of the bi-unit parent domain, it gets to be very convenient and very clean to define basis functions over each element. However, we can step back and take the global picture, right, and recognize that by putting together these local functions, local basis functions from the elements adjoining each node, we can actually construct these global shape functions, global basis functions, right? If we do that, what we observe is that the type of basis functions we are using here are ones with compact support.